This lecture is an introduction to the material that we're going to cover in this course in the context of an important and familiar application. We're going to try to give you some idea of what computer science is all about as a prelude to all the material that we're going to cover in this course. Let's begin with a brief introduction to what computer science is all about. Very basic question, what is this course about? Well, it's a broad introduction to computer science. Our goals are first to demystify computer systems, to give you an understanding of what goes on inside the computer that you use. Second, to empower you to exploit available technology. Whatever endeavor you choose, you're going to be using a computer, and people who know how to use computers effectively are going to be much more successful in their endeavors than people who don't. And the third one is also important, and that is to build some kind of awareness of the substantial intellectual underpinnings of computer science. This is often overlooked by many people who dive in to make use of the technology without really understanding that computation has been studied intensely by researchers of all stripes for decades. And there's quite a bit actually of understanding of what computation is all about, way more so than in some other sciences. So the topics that we're going to consider first of all is programming in Java. In order to really understand what computer science is all about, you need a broad facility in the ability to program in Java, in some programming language, and we picked Java. Fortunately, this is also very useful in a practical sense because programming in Java is something that you can use effectively in all kinds of future endeavors. We're going to talk about the design and architecture of computers, how they are actually built down from the smallest component up to the biggest computer. Seems like an ambitious goal, but as you'll see, it's possible for us to explain to you really how the computer is put together. And then, as I mentioned, we're going to talk about theory, about the whole idea of the theory of computation and what computation means and how it relates to the natural world. This is a beautiful theory that had been developed starting in the 1930s and also has really important practical implications. And all of these things we're going to do in the context of actual applications in science, engineering, and commercial computing. We don't use toy problems, we use real problems to illustrate the basic principles that we want to cover all across the board, whether we're talking about programming or architecture or theory. And so every lecture that we cover will have some coverage of important application. We don't do toy problems. Not just science and engineering, art, music, finance, many other fields. Computation really touches everything nowadays, so there's no shortage of application. I want to get people thinking about what computer science really is about. I want to start with a quote by D0aN2TIcBLs, who's one of the earliest and most famous computer scientists. And he says, "Science is everything we understand well enough to explain to a computer." Some people say, well, why is it computer science? What's the science in computation? And we'll definitely cover that. But I think the interplay between computation and science nowadays is very well established. There's many opportunities to take an understanding of computation and develop that into a better understanding of the natural world. And in fact, we have another famous quote from a famous scientist that everyone knows. Pretty early on in the life of computation, said this: "Computers are incredibly fast, accurate, and stupid. Humans are incredibly slow, inaccurate, and brilliant. But together they're powerful beyond imagination." That's really what we want to talk about in this course, is the ways in which people can exploit the incredible development of computation over the past several decades. The application that we're going to use to introduce basic principles of computation is from cryptography. It's called secure communication with a one-time pad. That's the starting point. So let's suppose that we want to arrange a system to allow for someone to send a secret message with a cryptographic key. And we'll talk about what this precisely means right now. So we have a character, Alice, who wants to send a message to another character, Bob. And these characters will reappear often throughout our lectures. So the way that we'll start is that sometime in the past they exchanged something called a cryptographic key. And this cryptographic key looks like a random sequence of letters, and it needs to be that in a very precise sense that we'll address later. So Alice says, use this key, which is listed in red here, if I ever want to send you an encrypted message. So maybe Bob writes it down on a piece of paper, but somewhere separate from the channel that's going to be used to send the message. Now, it's best to think of it done outside of any electronic device, written on a piece of paper. So then when it's time to send a message, Alice uses the key to encrypt the message, to put it in a form that a third party seeing the encrypted version couldn't understand it. And Bob then is going to use the same key to decrypt the message. So the fact that both of them know the key means that those are the only people that know what's in that message. So what we want to first establish is the idea that we can build a system that does this. So you can think of it maybe in the chat application on your phone. Alice would say, hey Bob, here's a secret message. And Bob would see that on his phone. And then it'd say, hi Alice, okay, I'm ready. And Alice would see that. So then a secure chat system, and you've probably done this in various applications, will ask for a key or a password. So that's when Alice types in her secret key. And then she types in her message. And what the system on her phone does is convert that secret key into some other sequence of characters that looks equally random. So that thing is sent in the clear, so we assume that anybody could read it. It goes outside Alice's device through some wireless system or wherever, and then eventually comes to Bob's device. We assume that anyone can intercept it and read it. So Bob gets that encrypted message, and then his system asks him for the key, and he takes out the piece of paper that Alice gave him in the past and types in the key, and then Alice's message appears. That's the idea. That's the system that we want to try to support. Now, clearly, the critical point of this is that without the key, any eavesdropper, and in cryptography it's traditional to use the character Eve as eavesdropper, can't understand the message. She can read what got sent in the clear, but she can't understand the message. So the first question we want to address is, how does this system work? How can we build a system like this? So our goal is to design a method to encrypt and decrypt data. So we have a message, send money. We want to encrypt it to get this message that we can send in the clear that seems to make no sense. And then we want to decrypt that to get the original message back. And there's been a lot of systems that have done this throughout history. One important example is the so-called Enigma machine. There was German code in World War II. And actually that code was broken by one of the first applications of a computer. The English mathematician Alan Turing built a computer in order to break the code, and that code actually was a turning point in winning the war. Another example that was important also historically is called a one-time pad, and that's the one that we're going to talk about next. And a third example we'll talk about later in the lecture is using a linear feedback shift register. So those are the two that we're going to talk about in this lecture. Now the first idea is that, and doesn't need much explaining nowadays, is that all information nowadays is encoded digitally. So that means we have a basic unit of information called a bit that can have one of two possible values, either 0 or 1. And the reason that we do that in so many applications and devices is that it's very easy in the physical world to represent two possible values in all different types of physical realizations. So you just think of 0 as being off and 1 as being on. And that's the basic abstraction that we start with in so many digital devices and computers. In fact, nowadays we really represent virtually everything as a sequence of bits. And this is very familiar to people nowadays because so many of the devices that we use every day with photographs and music and videos and so forth, all are encoded digitally as sequence of bits. Not that long ago it wasn't the case, but now it is. So what we're going to talk about in this lecture, for purposes of simplicity, is text. And we'll give some details about that, but even numbers. So for example, we can represent a decimal number 69 in binary as 01000101. And we can represent that in the physical world as a signal that goes from off to on, off, 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 on, off, on. So then any numbers, and then we can have codes for real numbers and so forth, and we'll talk about that. And later we'll talk about sound. When you download a song and it's an MP3 file, that's a digital file, a representation of that sound as a sequence of bits. In pictures and movies, and we'll look later in this course at these things in more detail. And actually, one of the most profound ideas is that you can represent the programs that we write to control computers as a sequence of bits, and that has amazing implications that we'll talk about in detail when we get to theoretical computer science. So the bottom line, again, which is fairly easy to motivate nowadays, is that if we can send and receive bits, we can send and receive pretty much anything that we want to send nowadays. Okay, so, well, you can't send a cat or a car, at least not yet. Maybe Star Trek comes true, you could. Okay, so let's just worry about text now. So that's our application with messaging, say, on a phone. So we're going to use a very simple code for this lecture just so we can do complete examples called the base 64 encoding. And what that does is provide us a way to represent the most commonly used characters, uppercase letters, lowercase characters, lowercase letters, numbers, and a few punctuation symbols. As sequences of bits. There's 64 different symbols, 26 capital letters, 26 lowercase letters, 10 digits, plus and slash. And that means we can represent each symbol with 6 bits, starting with 000 and working up to 11111. This is the binary number system, just going from 0 to 63, 64 different symbols. You don't have to worry that much about the binary number system. Just think of this table. If you have a symbol, you can get the sequence of bits. If you have the sequence of bits, you can get the symbol just by referring to this table. The methods used on your computer nowadays are just similar codes. They just use more bits so that we can use more symbols. And we'll talk more about details of those later in the course. For now, just think of it as a table. So ASCII, for example, uses 8 bits and can do 256 different symbols. And Unicode, which unifies for languages that have many more symbols than English, allows for 65,536 and more, actually, different symbols. So same idea, just more bits. So let's just think about it in terms of this table. So let's say we have Alice's message, send money. So we want to convert that to a sequence of bits. We look up capital S in the table. Capital S is 010010. So that we just write that down. Then we look up capital E, and that's 000100, write that down. And so forth. For each letter in the message, we put 6 bits in the output. So that gives us a way to encode any character string made up of one of these 64 different symbols as a sequence of bits with 6 times as many bits as there are characters. So that's a straightforward process. So now let's talk about one-time pads. So a one-time pad is a cryptographic key. This is what we want for Alice and Bob. That's known only to the sender and receiver. And a good choice for a one-time pad is a random sequence of bits. And we have to talk about what that precisely means. But let's say that we can have access to a sequence of bits where each bit is equally likely to be 0 and 1. So security depends on, first, the sequence of bits actually being random, and second, each sequence is going to get used just once. If you use the sequence multiple times, then it's not so secure. And I'll talk about why in a minute. So, so the thing is, one-time pad, so let's say we have this sequence of bits. So one thing to note is that when it's not convenient to work with sequences of bits, so we can actually decode that sequence of bits using the table back into a sequence of characters. Just use the same table and look up the first 6 bits and we get lowercase y, and the next 6 bits we get a capital T, and so forth. So that sequence of bits, we can more economically express it as that list of 9 characters, 54 bits, 9 characters. So that's our starting point, random bits, and then we convert them into characters. That's the cryptographic key that we're going to use for Alice and Bob. So now let's look at how encryption works. So as we just mentioned, we're going to have a random sequence of bits and convert them to characters. That's what Alice tells Bob to write down on his piece of paper. Or we say, send it through a secure channel. And so maybe it's a trusted courier or some other mechanism. Okay, so how do we encrypt? So the first thing is to take the text that we want to send and encode it as a sequence of bits. We already showed how to do that. And then we're going to take enough bits from the pad. In this case, we set it up so the number of bits in the pad that we used as an example is the same as in this message. If you have more bits, you just take the first n bits. And that's an important point. If you have a really long message, then you're going to need a really long pad or a really long sequence of random bits. And that's going to be a barrier that we're going to have to overcome later on. And then what we're going to do is have a very simple machine, a simple computing device that just works with sequences of bits and computes a new sequence of bits, taking the message and the pad as input. Very simple machine, and we'll look at how that machine works in just a minute on the next slide. And that's going to produce a sequence of bits, again, n bits. And then we can take that sequence and take 6 bits at a time and get a sequence of characters. That's the encrypted message that we're going to send out in the clear and even assume that the eavesdropper can see that message. That's called a ciphertext. So that's the encryption process. And any communications device, your phone or tablet and your computer, is going to have an encryption device like this. And even before computers, like the Enigma machine is not a not so simple machine that did the same thing. Take bits as input, take a cryptographic key as input, and produce a ciphertext as output. And one we're going to look at is very simple, depending on the idea that the one-time pad is a sequence of random bits. So let's look at what a simple machine like this would look like. So what we're going to do is, again, encode the message in the pad in binary. And now we're going to have a very simple machine that proceeds through these sequences of bits, 1 bit at a time, taking 2 bits as input and producing 1 bit as output. And the function that it's going to use to do that computation is called the bitwise exclusive OR. Exclusive OR of 2 bits is 1 if the bits are different and 0 if the bits are the same. So let's watch our machine. So the first bit is 0 in the message and 1 in the pad. Those are different, so the result, exclusive OR, is 1. We go to the next bit. They're both 1, they're the same, so the ciphertext bit for that position is 0. Both 0, they're the same, so the result is 0. Both 0, result is 0. Both 1, result is 0. Both 0, result is 0. So this is quite a simple machine, just taking 2 bits as input, checking whether they're different or the same. Now they're different, the result is 1. And it goes through the message in the one-time pad, 1 bit at a time, producing this kind of result. So after a while, we can speed it up a little bit. And you can see how with this very, very simple machine, we can compute a ciphertext from a message and a one-time pad. And then we can decode that ciphertext, as just mentioned, and get a sequence of characters that correspond to the ciphertext. So that's the machine that we're going to use for encryption. Message and one-time pad, bitwise exclusive OR to compute the ciphertext. So that's fine. We took our message and converted it into something that makes no sense. But let's make sure, and certainly if you want to study this material, you should think about how you would do some examples to make sure that you understand this process of encryption. So just to test your understanding of this process, you should try some small examples. So here's just one. Say we have a 4-character message EASY, and we have the pad 0, 1, 2, 3. That's not random, but the process works for any pad at all. So the process is to take our message, use the coding table to encode each character into 6 bits. And same thing with the pad, encode it in 6 bits. And then do an exclusive OR to do the encryption. 1 bit at a time, bitwise exclusive OR. Notice in this case that since the letter A is all zeros, the exclusive OR of that with 1 gives the same result, 1. And then decode, again using the table, and that's the encryption with the one-time pad. So it's worthwhile to try other examples from the book site or just make them up on your own. Okay, so that's all fine. We have a way to send a message with a secret key, but we haven't addressed the question of how does the system actually work? How do we actually get the message back? Alice's device uses the bitwise exclusive OR machine to encrypt the message. How do we get the original message back from the encrypted version? What kind of machine are we going to need over on Bob's device to get that thing decrypted? And the answer is the same machine works. That's a beauty of this system. So let's take a look at that in more detail. So now we've got a ciphertext, and we've got the one-time pad, the same one-time pad that Alice used, and now we want to get the message back. So we got the ciphertext that Bob's phone has received the ciphertext from Alice, and Bob typed in the one-time pad they have written down on a piece of paper. And so again, we'll use the binary encoding as before. And again, we'll use the same process, run our machine, taking the bitwise exclusive OR of the bits in the ciphertext in the pad. So they're both 1, the result is 0. They're different, the result is 1. They're the same, the result is 0. Exactly the same process, taking the bits 2 at a time and producing a resulting bit just by checking if they're the same or they're different. They're the same, now they're different, now they're the same, so it's 0, and go through and finish the process. So our machine, that same machine, is going to produce a sequence of bits. And now, if we use the table to look up those bits, we get back the original message. It's a little bit of digital magic, a really simple example of digital magic, but still digital magic nonetheless. So let's take a look at why it works. Alice sends her message, one-time pad. Eve can see the ciphertext, but it looks like gibberish to her. But Bob runs the same key through the same machine and gets the message back. Well, what we want in this system, it's all fine, but what we need to be able to prove is that the decrypted message is the same as the original message. As long as the XOR machine's the same, as long as the cryptographic key is the same. So just in math notation, if we let M be a bit of the message and K be the corresponding bit of the one-time pad, we want to prove that if you take the exclusive OR of M and K, these are just bits, and then that's a bit, and then we exclusive OR that with K again, then we get M back. This is just a little algebraic notation for exclusive OR. And we'll come back to many more complicated and profound applications of logical formulas like this, but this one is quite easy to understand just in the basis of what we've talked about. So if M or K are different, then the result of that is either 0 or 1. Is that different than K, then we get M. And we'll just look at two quick proofs of this. The first one is called a truth table proof, and this is an important technique that we'll talk about later in the course, actually having to do with design of computers. And the idea for that is to just write down all possibilities. So these are the four possibilities of the values of the two bits, M and K. Either they're both 0, or M is 0 and K is 1, or M is 1 and K is 0, or they're both 1. So let's look at the value of the components of this expression in all four possible cases. So exclusive OR of M and K is 0 if they're the same, 1 if they're different. So 0 in the case they're both 0, 0 in the case they're both 1, otherwise 1. Now we take those bits and again, applying the same definition, take those two columns and compute the exclusive OR of the bits in those columns. So in the first row, they're both 0, so the result is 0. Second row, they're both 1, so the result is 0. They're the same. Third and fourth rows, they're different, so the result is 1. But now that column is identical to M. That's a proof that M exclusive OR K, the quantity exclusive OR K, is equal to M. That's the quantity that we want. You can also prove this with something called Boolean algebra, which is a little bit more formal system, and again, we'll talk about this when we're talking about the design of computers. So a bit exclusive OR with itself is 0. The bit's the same as itself, so the result is 0. A bit exclusive OR with 0 is just that bit. If it's 0, the result is 0. If it's 1, the result is 1. We already noted that. So then we can redistribute the parentheses, M exclusive OR K, quantity exclusive OR K, we can move the parentheses to say that's M. You don't have to prove that, but it works in this algebra the same way it works in the more familiar algebra. And so that K exclusive OR K is 0, that's M exclusive OR 0, the result is M. So it's two ways to prove that it works. Try all the cases if you want. Learn about Boolean algebra if you want. We're going to do both later on. So that's the magic of a system that allows for secure communication using a one-time pad with a very simple machine. And this system is useful for many years for lots and lots of applications. So now there's another crucial thing let's make sure that we cover, and that is that Eve can't read the message without knowing the pad. She might have a guess, or maybe she stole Bob's piece of paper or took a photograph of it or something. But the thing is, if she doesn't have the right cryptographic key, the wrong pad, we can even assume that Eve knows about the machine. She's got one of the machines, she took it apart and knows exactly how it works. And that's typical in cryptographic systems because you can steal the machine, somehow know how it works, but you might not, you're not going to know what the cryptographic keys are. So she could run through that, but she's still going to get gibberish out as a result, not the original message. Only way to get the original message is to have the right cryptographic key. In fact, that's provably secure, and that's a result due to Shannon, and he's father of information theory and many other contributions we'll talk about later. If each pad is used only once and the pad bits are random, then there's no way that Eve can know she can't tell the difference between the ciphertext and random bits. And that's a very important and profound result that's at the basis of this kind of cryptography. Now, the thing is, though, you might say to yourself, well, Eve's got a computer. Why can't she just try all possibilities? She's got a room full of supercomputers. She's got 1 billion computers on the cloud nowadays. Why can't she just go through all possible pad values, go ahead, run them through the machine, and there's that bad one, and eventually she'll stumble across the pad value that gives the message out. Wouldn't that work? Well, there's a problem with that. So one problem is there's too many different values. There's 2 to the 54th possible pad values, and 2 to the 54th is a huge number even for a computer. If Eve could check 1 million values per second, and that would be a lot, it'd still take over 5 centuries to check all the possibilities. But that's not even the problem. The much worse problem is that there's also 2 to the 54th possible messages. So if she were going to check all the pads, she'd see all possible messages. And there's no way to tell which is the real one versus any other one. So she says, oh, new tattoo, maybe that's what Bob's trying to say, or whatever else, anything else that you can express in 9 characters. No way to distinguish the real one from any other one. So this approach just doesn't work at all. That's how we say the one-time pad is provably secure because of randomness in the cryptographic key. The good thing about one-time pads is that they're very simple. You decrypt with the same method, provably unbreakable, and it's widely used in practice. During the Cold War in the 50s and 60s, the hotline between the White House and the Kremlin was a cryptographic system based on that, and they had people had books of one-time pads that were transferred from one capital to the other by trusted couriers. One problem is you can't reuse the seed. You have to actually destroy it. Another one that's important is it's hard to find truly random bits. We'll come back to that a little bit. And nowadays, Alice wants to send maybe a whole video, a gigabyte or more. Bob says, well, wait a minute, where are you going to get the 8 billion bits that you need for the key? And how are you going to distribute it securely, separately? And how it's got to be as long as the message could be a huge, huge message. And Bob says, well, I don't have enough room for both the video and the key, let alone multiple keys if you're going to send me multiple messages. So we're going to talk about the 2 problems, at least address those in this lecture, is what about the random bits and how do you deal with the problem that the pad has to be as long as the message. Well, where are you going to get random bits? Well, you could look on the internet, and you can look and find sites like this, random.org. And you can type in how many integers you want. You can say, I just want between 0 and 1. and fill in whatever it asks for, and you get some random bits. So it says that it gets the randomness from atmospheric noise. Well, it could be, but maybe that's something that Eve made. So maybe that's not a great place to get random bits. What we're going to talk about next is a way to create a really long sequence of bits that they're not random, but they're hard to distinguish from random bits from a short key. And that's the way that we're going to address the defects in the one-time pad cryptographic system. So that'll be the topic of our next section. So the method that we're going to use to generate long sequences of pseudorandom bits from a small key is known as a linear feedback shift register. It's a machine like our XOR machine, just a little bit more complicated. It's called a deterministic machine that produces a long sequence of pseudorandom bits, and we'll talk about what that means. The Enigma itself is actually an example of such a machine. It had some settings in the machine that were much shorter than the length of the messages that were sent. The one we're going to talk about is linear feedback shift register, and those are used for a while, and there's many, many others that people have studied. Actually, research is still ongoing on good methods for doing this. Initially, this is a quote due to John von Neumann, who's another character who's going to come up often in this course, because he conceived of the design of the computers that is still used on all computers today. And this idea of needing randomness came up very early in the study of computation. And what von Neumann said is that anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. And what he meant by that is it's not really random. It looks random, but it's not random. So let's look at what these words mean. So deterministic means that if the machine's in some state, we can figure out what the next bit is. It's determined, well determined what the next bit is. That's almost the opposite of random. For a random sequence of bits, we don't know what the next bit is. But it's an absolute requirement for our encryption application, because we need to know that Bob's going to get the same sequence that Alice put in. So that's a tension that definitely informs the designs of these types of machines. So by pseudorandom, we mean that Eve can't tell the difference between this sequence of bits and a random sequence of bits. It's not something, we can never actually achieve the goal of randomness, but we can make our sequence of bits to be sufficiently complicated that anything that we think that Eve might try to understand the sequence is not going to be feasible. So what does that mean, appears to be random? It's a very profound and elusive concept. So for this lecture, we're just going to say has enough properties of random sequence that Eve can't tell the difference. And we'll get into the implications of this idea a little bit more later on. So just for example, Eve might say, well, if there's 100 bits and then the same 100 bits immediately after, that's not going to appear to be random. It should have about the same number of zeros and ones. It should have about the same number of 00011011. All kinds of things that you could think about that you would try to study to see if you think that sequence is random or not. Those are the types of things that we want to make sure our sequence of bits pass those kinds of tests. So like just examples. Does this sequence look random to you? No, it's all zeros. What about that one? No, they alternate 0, 1. But if our criterion is that the number of zeros and ones should be about equal, it passes that one. So we have to be a little bit more. What about this one? No, that one's not at all. That's, if you look at it a little bit, it's got some longer repeating patterns, but the numbers of pairs 0, 0, 0, 1, 1, 0, and 1, 1 are about equal in that sequence. What about that one? That appear to be random? Nope, that's our encoding of send money. That's not random, that's our message. What about that one? Does that appear to be random? Well, that's the key that we gave Alice and Bob, and we generated that actually from the method that we're going to talk about. What about that one? Well, that's the ciphertext that our XOR machine generated. And our claim is that Alice is not going to have trouble telling the difference between that and a random stream. What about that one? That one I actually generated by flipping a coin. So I hope it appears to be random, or there's something wrong with my coin. How does that one look? Does that look to be random? So that one asks the student to type some random bits in, and that's what they came up with. And actually, it's a famous application of probability theory that that a random sequence of zeros and ones is going to have some long sequences in it. And humans, when you ask them for random bits, tend to not type in long sequences. So you actually can, if you ask a person to type in some random bits, you can actually tell the difference between that and a random sequence. Now, of course, it's important to note that if you get your bits from atmospheric noise or wherever, it is possible, if they're truly random, that they could all be zero, or they could be any one of these sequences. So again, it's worth thinking about what randomness really means. So let's look at our method for generating a long sequence of pseudo-random bits. It's called a linear feedback shift register. A little bit of terminology, so we talked about bits. So our machine holds bits in cells. It's a little storage element that holds one bit. A register is a sequence of cells. So this is a register with 11 bits in it. And we have a thing called a seed. That's going to be our short key. It's an initial sequence of bits that are stored in the register. And this machine is based on feedback. That's the second word in its name. And what the feedback for this example is, we take two bits, the ones in position 11 and position 9, and we exclusive OR them together and put the result to the right of the register. So in this case, the two bits are 0 and 1. They're different, so the result is 1. And shift register means there's a ticking clock. Every time the clock ticks, we move the bits one position to the left. The bit that was in the leftmost position drops off, and all the other bits move over one position, including the one that we just computed. And that's the essence of the machine. We keep running that machine, and the bits that flow through are pseudo-random bits, and we'll look in more detail at it. So the bit positions that we choose to do the XORs are called the taps, and one of them should be the leftmost one. We number from the right starting at 1. The new bit position is number 0. And we refer to an NK LFSR as an n-bit register with taps at n and some other position k. So this is an 11-9 LFSR. And it's important to note that not all the values of k give the effect that we want, and we'll talk about that in just a minute. So let's do a simulation of the operation of a linear feedback shift register with these initial contents. So we take the leftmost bit and then the one position off and exclusive OR those, and that gives us a 1 because they're different, and then we shift. And we'll keep track of the history of the register contents, so after one clock tick, that's our new contents. Everything's shifted over. The leftmost 0 shifted out, and the new 1 shifted on at the rightmost position. Now we do the same process. Those bits are different, so we get a 1, and then we shift. The leftmost 1 drops off, the new 1 comes in, and that's our contents of our register at time 2. Continue in this way. Now those are the same, so our computed bit is 0, and then we shift left, and that's our register at time 3. So continuing in this way, we get a long sequence of register contents. Now the bits are shifting through the register, so really we're just interested in the sequence of bits that are created. And that's the sequence of bits that Eve's going to have trouble differentiating from random. Very simple process. It's almost the simplest non-trivial machine that you can imagine. But it manages to do this job of producing sequences of bits that appear to be random. So we just look at that sequence of new bits that we compute, and it turns out to have many of the properties of random bits. It's kind of amazing that we can get such a result with such a simple machine. So you can say, here's a really long random sequence, and you can study that sequence, and we'll ask you if you think it's random or not. And Eve can study it and look for all the things that she thought she could use to tell if the thing's random. And there's many, many more things that you can try. It looks pretty random. But it's actually, that's the one-time pad that we used in our example. This thing was created by our 11.9 LFSR with the initial seed 011010010. So it's a pseudo-random sequence, except maybe some observers, and we'll get back to that in a minute. To test your understanding of how LFSRs work, try solving problems like this one. This exercises all the definitions that we just went through. So 5-4 LFSR is going to have 5 bits, the tap positions of the 2 leftmost bits. And then you can just write down a table taking the 2 leftmost bits, produce a new one, and then shift over 1 position and keep going. So that's an example of testing yourself on how well you understand what an LFSR is and does. So how do we use the LFSR for encryption and decryption? So the key idea is that the seeds are going to be short, only the number of bits in the register. So you can have a huge number of seeds, and in fact, I have a book of random seeds that Alice creates, and those should be random as best we can, just like the random bits that we ask for the one-time key. And then Alice just gives that book to Bob. And so when it's time to send a message, Alice will send some kind of description of which seed to use in that book. So like the next one, last time I sent you a message, we used some seed, just use the next one. And it's going to be a short seed, some entry in the book, but now my secret video is 1 gigabyte, and Bob looks up and says, okay, now I have the short seed that I can use. So they both use the specified seed to initialize a linear feedback shift register and produce n bits. Since the machine is deterministic, they give it the same input, they're going to get the same output. That output is pseudo-random, so now it can serve the same function as the one-time pad. It's just it's way longer than the seed, and that is a big advantage. So now we can, Alice and Bob's machine can both use the LFSR and the XOR machine in the same way in the cryptographic system. And what Eve gets is still the same bits that appear to be random to her, as long as the bits produced by the LFSR are sufficiently close to random that Eve can't tell the difference. that simple machine reduces the burden for Alice and Bob of long seeds and dealing with large numbers of random bits. So but what about Eve's opportunity now? So she's got computers, and again, we're going to assume that she even knows they're using LFSRs and what the taps are. Why not try all possible seeds? The message is really long, but the seeds are short. And the thing is that if you try all seeds, you're only going to get a tiny fraction of all possible messages. And so it's reasonable to conclude that most of them will be gibberish. Only the real seed is going to give a message that contains maybe words that you could look up in a dictionary or recognize as a real message in some other way. And the good news for Eve is that this approach can work. So for our 11-bit register, there's only 2,000 possibilities, so it would take her no time at all to go ahead and try all possibilities and see if she can find a real message. So very likely that only one of the messages is not gibberish, and really after little time in this course, you can write a program to do this. Really, you could, and many of you, I'm sure, will try. But the bad news is that this problem scales for Alice and Bob, but not for Eve. It's really easy for them to use a much longer linear feedback shift register, which changes the situation for Eve. And just to see that, let's talk about just a couple of key properties of linear feedback shift registers. First one, a basic one, is can't use all zeros as a seed, because 2 zeros, they're the same, so the result is 0, and all that does is produce zeros. So no good. So another thing is that to realize is that it's eventually going to cycle. There's 2 to the n minus 1 possible values of that n-bit register. The minus 1 is for the 0, otherwise all possibilities are possible. Future outputs completely determined by the current fill, so once a fill value repeats, then the same thing is going to happen over and over again. And it can't be infinite, because after you've gotten 2 to the n different ticks of the clock, then there's more possible fills, more fills that you've seen than possible fills, so there has to be a repeat in there. So this is just an example. This is a 4-3 LFSR, and we click for a while, and before too long, we get back to the value that we started with. So after, in this case, after we get all 15 possibilities, and we get back to the value that we started with. That's actually a good case. It's not always the case that it'll fill all possibilities. The cycle lengths depend on the tap positions. And for a long time, people studied what tap positions you need in order to get the full cycle length like this. So if you, for example, if you do a 4-2 LFSR, then it repeats after only 8. It's not the full cycle. So again, an extremely simple machine, just defined by 2 parameters, but requires some pretty advanced mathematics to really understand the behavior of this machine. That's one of the key concepts about computation that I want to introduce with this example. You can have a very simple machine that can have quite complex behavior. You need finite groups in order to understand this one. Bottom line, with the internet, you can find manuals and books out there that tell you for a certain number of register size how many bits that you get. So that's where we found 11.9 gives 2 to the 11th minus 1. And if you do a big one like 63 bits, then you can get 2 to the 63 minus 1 cycle length, which is huge. So very easy for Alice and Bob get a full cycle position and then know that the thing is not going to repeat until after 2 to the 63rd bits. When it repeats, it's not going to look random. And long repeat is one of the first tests for is something random. But if there's fewer than 2 to the 63 minus 1 bits, then it's going to look random. So now that creates a problem for Eve, because she can try doing all possible seeds, but there's way too many possibilities. 2 to the 63 minus 1 is a huge number. That's called exponential growth. And it doesn't matter how fast computers are, how much faster computers are getting or how big they are. So for this example, it'd take her almost 3,000 centuries to try all seeds at 1,000,000 seeds per second. And 63 bits is a tiny, tiny amount. Alice and Bob could go to a 128-bit register or a 1,000-bit register and get to impossibly hard task for Eve. Just not enough computers. And we come back to this idea of exponential growth. It's an extremely important concept in understanding really what's possible with computers. Now, just a footnote, there's bad news for Alice and Bob that the LFSR output is I want to finish by talking about some implications of the application in the machines that we've looked at. There's the linear feedback shift register in the general computer. They have really important similarities. They're both built from very simple components, and we'll see that in this course. So we have to be able to control it. So LFSR, that's start, stop, and load it with a program. They have a clock that ticks along, and it does something every clock tick. They both have memory. Of course, the computer has way, way, way more memory than the LFSR, but they both have memory. They both take input. and wherever it comes from, LFSR just takes a little. The computer might take a lot from the internet or some other kind of device. They both do computation. They take bits, functions that take bits as input, produce bits as output. And the ones on the computer are way more complicated. And they both produce output. The LFSR produces that one specific kind of output, and the computer can produce any output that any computer can produce. And we know that in a specific theoretical sense that we'll talk about much later. So they scale to handle huge problems, both of them. Even the simple LFSR can handle a problem of sending a movie or billions and billions of bits. And they both require careful study to use effectively. You can't just pick an arbitrary tap position for an LFSR. You have to have some kind of understanding to know what tap position to pick. And of course, for computers, you have to have some understanding of what to do in order to get it to compute what you want. There are some big differences. So computer takes a lot of input, has a lot more operations, but you'd be surprised how little those differences are. They're simple computers that really are just slightly different from LFSRs. That's one amazing fact that the theory tells us. General purpose computer can simulate any machine, including LFSRs, and they all have equivalent power, and that's what we'll talk about in the theory section. That's really a profound idea, and that's what programming is all about. We can write a Java program to simulate the operation of any machine that we can imagine. That's really a basis for our understanding of computation. And that's how our real machines got into existence. We imagine a new one, and we study it by simulating it, and then we use our existing computer to help build the new one. We're going to cover all these sorts of issues in this course. For now, just think about the idea, and this is a program that you could write after a few lectures. And that's a Java program I'm not going to talk about now, and that's what we use to produce the bit sequences that we talk about in this lecture. We didn't actually build that imaginary machine. We wrote a program to simulate its operation. And any machine you can imagine, we can write a program to simulate its imagination, its operation. That's an extremely profound idea. And you're going to be writing code like this very soon. We have touched on, just in this early example, some really profound questions that we keep coming back to. So one is, what is a random number? The LFSRs do not produce random numbers. They're deterministic, and that's why von Neumann said you're in a state of sin to try to do this. It's incompatible with random. It's really still, though, it's not obvious how to distinguish the bits LFSR produces from random, but experts have figured out how to do so. So that's why people study other methods of producing sequences that can't be distinguished from random. But really knowing what's random in the real world is really a profound question. Are there random processes in nature? If we could get some bits from atmospheric noise, would they actually be random? Or maybe subatomic particles or mutations in DNA, are those things actually random? So it's a very profound question worth thinking about. Is the whole natural world some kind of deterministic machine? If we had enough computer power, could we figure out what's going to happen next based on what's happening now? We'll finish off with another quote from Einstein, who says, "God does not play dice." And that indicates maybe what he thought it was thinking about computation and the idea of determinism in the natural world at that time. That's our introduction to computer science, and we look forward to starting in on the rest of the course soon.